Hello, and thank you for joining us for today's event, How Propane is Evolving for the Future. During this event, all participants will be in a listen-only mode. To ask a question at any time, please submit your question via the chat box located in the lower right-hand corner of your screen. We encourage you to ask questions at any time during the presentation. Your questions will be addressed when possible. This event is being recorded. The recording and presentation will be available on the Engine Technologies website shortly after the live event. I would like to introduce today's speakers. Alan Schaefer from the Engine Technology Forum, Gav Hale with the Propane Education and Research Council, Eric Suits with K-Tech Engineering, and Shrinu Gunturu with Stanadyne. And now I'll hand it over to Alan, who is our Executive Director of the Engine Technology Forum. Alan?
Thank you, Josie, and good afternoon, everyone. Delighted to have you with us here on this May 1st day. We have an exciting program yet this afternoon, so really appreciate your attendance. A quick word about us. After 23 years as the Diesel Technology Forum, we have evolved to the Engine Technology Forum. And this is a little bit about our organization, which focuses on research, education, and outreach, today being a really good example of that. The members of the organization are listed here, and we thank all of them for their continued support and sponsorship of today's event. I'd like to just maybe set up our session here just quickly and talk a little bit about how we see internal combustion engines and how they fit in the clean energy future. And we do see that they fit actually quite well. I think everyone on this event is no doubt familiar with the great diversity of engines that serve our society today in any variety of purposes, whether it's goods movement, delivering things to our grocery stores and all of our needs by highway or rail, boats and barges by marine application. Agriculture, construction, industrial, and power generation uses all really rely on internal combustion engines. And those engines run on a wide variety of different kinds of fuels today. And that list might be even expanding for tomorrow. But one of those fuels is of our particular interest today, and that's propane. And as we see the world today, that the energy and climate challenges we have before us really are quite complex, and there's not going to be a silver bullet, not a single solution that's going to work for everything, everywhere, all the time. And that's what makes internal combustion engines continue to be very important in our society. With that, those engines and the technology underlying them needs to continue to evolve to make the engines more efficient, lower in emissions, and ability to help us achieve those decarbonization objectives that everyone is working towards. So that takes us to where we see the future for internal combustion engines. With that, I'd like to turn it over to Gav Hale to get us started with a broad look at propane. And Gav, thank you for being with us today, and we look forward to your presentation.
Not a problem at all. I can see I'm the presenter and my little arrows thing is lit up at the top, so it looks like I'm in control. So thanks for the opportunity to talk to you all today. And I've got quite a bit of material to go through, but it's graphical, and I'd like to move as quickly as possible to allow Stanadyne the appropriate amount of time. But what it seemed to be appropriate to do is to talk about the fuel and the infrastructure and how propane served today, to level set around that, because without that understanding, it just becomes almost like an isolated technology. So the mechanism, infrastructure, and value prop around propane today, leaning towards renewable propane, some examples of the current engine technology today, brief overview of some of the segments, literally a word or two on that, and then a lean into how we're reacting to the tightening limits, particularly associated with greenhouse gas and phase 3 limits that have been ruled by the EPA. So that's the general logic. I'm going to try and keep the pace up. I guess don't know what the logic is around questions if there's somebody puts their hand up or save it to the end, whichever works. So how propane is evolving. So firstly, if you're going to have, or if you're to talk about a relevant alternative fuel or alternative energy, what must that fuel be? What attributes must it have? May not exist today. Maybe something needs to be developed, but it needs to roll back to these. So number one, the energy source needs to be reliable. Needs to be able to navigate from a supply standpoint adverse conditions such as energy shortages or climate, weather. Capacity, there has to be enough of it to be meaningful in the marketplace that you wish to serve. And it must be abundant, otherwise, not just produced in one place. It needs to be able to be deployed nationally. Has to have an ability to reduce emissions versus today, but it can't come at the cost of affordability and being able to drive genuine commercial value. Energy, we have a responsible to have equity with the energy that we produce, and that energy should be accessible to different layers of society and the businesses that serve to support that. You can't have an expensive solution. It has to make sense. It has to perform as well as the original fuel source. So simplistically, if there's a diesel engine today and we replace it with a propane engine tomorrow, there needs to be a way to make that propane engine as efficient as possible, ideally to compete directly with diesel, and that leads to being uncompromised as well. So propane can enable all of this. Not everything all at once, everywhere. That's a journey, but there's line of sight to the right technologies to do that, many of which are actually in production today. So about propane, it's a US product. It's all made here in the US, 100% of it. And out of the total quantity of propane produced today, approximately 30% of that gets used domestically. The balance gets exported either into South America or over to Europe. So 100% US produced and used by, this isn't an all-encompassing answer, but it gives you an idea. 48 million homes in the US rely on propane for their heating and energy sources today, predominantly in places which are kind of distant from the grid or natural gas pipeline infrastructure. 900,000 farms rely on propane for grain drying, for power generation, for irrigation and water management. 600,000 forklifts use propane today all over the US. Propane gives a capability to give you great stamina through the working shift, but also to work indoors and outdoors. Huge market for us, and 30,000 school buses. That's a conservative number because where we struggle is we know production volumes, but what stays in service is sometimes difficult for us to see. So that number is probably somewhere between 30 and 40,000. And propane is a good source of energy for school buses because you achieve massively lower emissions versus diesel. You deal with a particular factor and you do it at a reasonable cost, particularly versus electrified solutions. And give or take, there's 115,000 generator sets sold annually in the US that go from the small portable Home Depot things that you put a £20 cylinder with it and walk away with it, through to larger product that's actually used for propane. There was a question just popped up in the right there that talks about kilowatts engine sizes. Hold that thought. There's a little chart we can walk through later on, so we will answer that question. I'm going to pick the pace up a little bit here. So advantages, this is exciting stuff. So when you think about the chemistry of propane, what does that mean to an end user? What can it give them? Well, its specific gravity is 1.52. What does that mean? Heavier than air. So if you're servicing a propane power vehicle in a workshop, the gas doesn't rise to the ceiling if it leaks, creating an issue with lighting. It sinks to the floor and there's a chance to evacuate through windows and doors. So if you've got a workshop today where you can service, maintain or build diesel or gasoline powered vehicles, you can move straight into propane without any additional infrastructure safety issues with that building, other than obviously needing to get trained on how to do it. So the heating value is 84,900 British thermal units. I do like that. So less than gasoline and diesel. So that's the trade-off. There's less energy in propane than diesel. but with the right engine optimized correctly in connection with this octane number of 105. So think about your regular pump gas at Citgo or wherever, that's 87 octane. Propane runs at 105. So what does that mean? Well, you can run the engine with a more aggressive ignition timing, which compensates for some of the lower calorific value. Limits of flammability. If it's lower than 2.4% or higher than 9.5% gas to air mixture, it's actually really difficult to ignite. I'm not going to say or recommend anybody try it, but it's difficult to ignite. So it's a safe fuel. And when we store propane, it's kept in a liquid form at 100 psi at 60 degrees. So it's easy to store, easy to transport, versus other solutions like CNG and hydrogen. How do you buy it? There's multiple different ways. There's actually now closer to 4,000 distributors of propane throughout the US, from large companies that have multiple outlets to, frankly, mom and pop shops that serve maybe some of the farm territories, particularly in the Midwest. Either way, it's easy to get hold of. And that, I said, 20 locations within 7 miles of here. Where is here when you're in a video conference? That's actually New Orleans. So downtown New Orleans is 20 places you can get propane. And a percentage of those are also able to refill a vehicle tank, so through our autogas network. So there's a good infrastructure that's already in place. If you're running propane in a vehicle, this is the current status of filling stations in the US. And where we tend to grow is because it's not like Europe, where you've got a lot of passenger cars with this fuel, but there's a lot of school buses, a lot of delivery vehicles that do a return to base. So some of those filling stations would be actually customer location. So there's probably way more than that's actually on the map. But on this map, these are places where you could go with your truck to fill up with propane. Pricing relative to diesel, it's always good when there's a saving amongst all this. So this is kind of up to date, but to be honest, probably need to update it because fuel's gone up a little bit this last 2 weeks or so. But you can see directionally where propane is an on-road fuel and the alternatives stack up. So yeah, this probably needs, the diesel needs to go up a little bit. So a definite economic advantage. As we said, there's a trade-off with efficiency sometimes. So there would be a diesel gallon equivalent factor in here, but typically we're still saving 50% in the fuel pricing. So propane currently is a fossil fuel that comes from the production of oil and gas. It's almost a waste product, and that's why we have so much of it. But we are also, the Education and Research Council, we're helping companies invest in methods to develop and produce renewable propane. So renewable propane in this context can come from the waste stock, used cooking oil, general waste products, or increasingly the viability of non-food crops to develop this. And the benefit of a non-food crop is you can be really honest about its carbon intensity, because when you use waste product, what was the heritage of that waste product? What does it take to turn it into a renewable product? And what was the penalty there in terms of emissions? With a non-food feedstock, then you kind of avoid that. So renewable propane is absolutely molecularly identical to the fossil fuel version. So any engine or vehicle you're running today with standard propane, renewable propane will work. This is one potential feedstock, camelina. It's basically a weed. It grows in drought conditions, wet conditions, and its yield of oil for each one of these nodules here is incredibly high. So this is a crop that's being sponsored globally for renewable propane production. It grows really well here in the US. And if you look at the carbon intensity of renewable propane, so conventional propane is 78 or so per grams of CO2 per megajoule. Renewable can be from 7, as low as 7. In fact, camelina is down towards that 7 rather than the upper, which includes a waste product. And if you look at the carbon intensity of the various states, we're significantly better even with conventional propane than the majority of states in the US right now. And remember, this is an average statement, it's not a marginal one. And a marginal one means at times of day when a state may be capable of achieving a low figure, but when its grid is under stress, brings in electricity from neighbouring states or uses other forms of power generation that aren't as carbon neutral. So this tends to be a big deviation. On average, here we've got 35, but during the marginal condition, it's probably 3 or 4 times that number. So that's something to bear in mind when you look at comparative carbon index. Projections of renewable propane production. This is a very crude graph, but we actually achieved this figure in 23, 4.5 million gallons, probably close to double that as we go through 24, ending up with 20, then it ramps up, and then the plan is to have the capability to meet the 10 billion gallons of, we'll call it fossil propane today, equal that with the renewable variety. So that program's on track. The challenge is to have refiners recognize propane as a viable fuel source within that renewable feedstock, because there's other products that can be made from the same feedstock. And that's PERC's job to help amplify that. So we work with the refiners to do that. So that's a little bit of background about the fuel. Now, thinking about some of the engines that are available for both on-road and off-road, and a lean into some of the development that's taking place to make propane a really viable fuel as we go toward and through 2027 for on-road. So the biggest opportunity for the propane industry and engine manufacturers, and the biggest opportunity for vehicle OEMs, is to find ways to address the complexity that diesel exhaust or diesel technology on-road particularly drives in terms of an exhaust after treatment and emissions limits. So from 2027, you get a combination of the conventional EPA regulations, but then greenhouse gas phase 3, which I've not gone into in any real detail here, but we've put a lot of work into what our approach is to that. And it really makes diesel a very, very difficult fuel, close to being non-viable for many on-road segments as we go closer from 27 through to 2030, which is the period of time where phase 3 is implemented. So vehicle OEMs are now actively seeking alternatives to diesel. So that's the opportunity for them. They get to reduce emissions with a fuel that's available and retain most of the design content of the truck, which is key because a lot of other alternative energy sources mean a big tear up for the OEMs. So we've got active programs with on-road OEMs, and I can't really get into much more detail than that. And we're developing our suite of engines with the engine manufacturers that are participating with us to develop engines for those applications. So this is the kind of technology you have for a diesel oxycat, SCR, ammonia slip cap, burners, registering and legislating for NOx, secondary DOC, other DPFs and secondary SCR system. So close to engine and underfloor, and that gives you the kind of span of technology to get the emissions correct out of the exhaust for a diesel engine. So your after treatment is way more complicated than your engine, really. It becomes the dominant factor. With propane, today, all you need is a 3-way catalytic converter, similar to the ones that you have on your car today. For 2027 regulations, probably 2 catalytic converters, close coupled under the floor if it's a truck. As we move into phase 3 greenhouse gas limits and our journey to 2032, then this really stays the key recipe, with potentially the addition of some of SCR potentially in the exhaust after treatment. But that depends on the balance of technology that we're able to deploy in cylinder to drive the best efficiency in the engine, rather than relying on the after treatment to catch everything. So that's a balancing act that we've got. And when we look at some of the options that are available to us, this is a relatively active program, and I suggest it's probably a pathway forwards in some shape or form. But this is to take propane to a compression ignition solution, we have viable work underway right now to do that. It then becomes an action of commercializing, but the engine manufacturers will love this because it's low technology, simple change to the engine, almost a drop into an existing engine design, maintain your existing supply chain, maintain your existing manufacturing processes, exceed emissions limits. And it is this sort of technology that takes us to efficiency that's equal to diesel. When you combine this with forced induction, supercharger, for sure, we will have to have supercharger option on some of the engines that we've got. We've got one that's got that, or turbocharging. So this is a game changer. This takes propane into a completely new dimension, because historically we've had to work with engine manufacturers that are a flavour of automotive. As we have to journey to meet the greenhouse gas limits. That brings in new technology like this. There's two major engine manufacturers that we're talking to at the moment about this, and a demonstration engine is already running. So this isn't science fiction, it's the economic delivery of science fact. So we dealt with the emissions. What's the impact on the vehicle? So for a CNG, compressed natural gas solution, huge tank, a lot of money, weighs a lot. Propane tank, because of the 100 PSI limit and the safe nature of the fuel, it's a $4,000 tank. So much smaller, much more compact tank. So we're meeting the emissions. We've got renewable propane that's coming, easy to integrate from a vehicle aspect to a fuel system, and it's a mature solution. So think of the school buses, the delivery vehicles that have solutions like this already in place. It's kind of not rocket science. What is rocket science is when we develop an agricultural tractor version of the engine that I was talking about, where do you put the fuel? That's always the elephant in the room. Where do you put the fuel? So we're investing in conformal fuel tank designs that would enable a propane tank to occupy a similar space to what is a diesel or a gasoline tank today. Filling up with fuel, what's the infrastructure implications? I kind of said it was a simple thing to do, but here's an example of a school bus refilling tank, a particularly large one for a large school with a large fleet. That installation, safety barriers, tank, electricity supply and canopy was $175,000 for the whole thing, installed by one of our propane retailers with a fuel supply contract. The equivalent for CNG, different ballpark altogether. So we've got the emissions, we've got the renewable elements coming in, the fuel system's easy to integrate with the vehicle, advancing technology, and a way to get the fuel from our marketer, a point of source to a vehicle, very, very cheaply. Refilling with propane is no more difficult than diesel, really. Maintenance facilities, we've kind of talked about that. Zero investment. If you build things today with internal combustions, if you fix them and maintain them or store them in a garage, you need to do nothing. The codes and standards that exist around propane are identical, as opposed to significant investment, say for a service bay, for a compressed natural gas solution. So easy adoption from a servicing standpoint, and the technology is way simpler than diesel. We've seen some of that. In terms of segments, I'm picking the pace up now because I can't take too much time. We said power generation, material handling, on-road and off-road, and here's some examples of some of those technologies. So Caterpillar with the forklift trucks, a company called Maffei that makes terminal tractors for the ports. That's a huge market. The ports have wholesalely adopted propane, backing off electrification, amplifying propane. Not in every case, but certainly the large container ports, they need a 24/7, 100% availability. Recharging isn't an option. So that industry is moving massively to propane. School buses are already there. Power generation, think about the simple exhaust solution, trying to package that in a terrible genset. Propane does that very well. Buses, we talked briefly about that. There's some paratransit type applications and some pricing, which I've got as public data, so we can share this. So gasoline solution, 71k, propane 86, and electric 233. And think about the savings in fuel that drive straight to your bottom line. I think by the time you've taken everything into account, it's 56 to 60 cents a mile saving, which is huge for anybody who's got a route that's delivering plenty of miles. That's a significant saving in fuel costs. In terms of existing engine offerings, I'm trying to lean back into that question that was asked earlier. Difficult slide to read, but this is really difficult to get on one slide. We've basically got, so blue is variable speed on and off road. Orange is significant power generation. So for the majority of on-road, we need a solution. This is in kilowatts. You can compare both together because power generation is kilowatts, obviously. Our horsepower requirement, if we can deliver propane solutions between 15 and 350 horsepower, then we've got things covered. And that's kind of where we sit today with the products that we've got. So if the question is how easy is it to displace a diesel model with a propane one, broadly speaking, it can be done. The danger is you can get into a swap volume trade-off, particularly if you're thinking take a diesel out, put a propane engine in. That's where turbocharging and supercharging are absolutely mandatory. The days of the naturally aspirated propane engine are significantly limited for many sectors, and that's where we're focusing our development. So as we go through our development programs with a view to 2027, that also gives us off-road capabilities in those power nodes. So I'm going to say simplistically, from a power standpoint, we've got it covered. Where it becomes questionable for off-road is the engine configuration going to give you the right power takeoffs and things for customers, and that can be a challenge. So it's a case by case thing. But simplistically, from a power standpoint, we're there. EV transition, propane, and where that intersects. So we're part of the wide path to emissions reduction. We don't necessarily compete with anybody because nobody can fulfill everybody's needs with whatever solution they're looking at, whether it's hydrogen, that's a long way off. EV, that's quite a long way off for many of the segments we work in, whether it's propane, diesel, or even gasoline. We're all part of the solution. But where can propane intersect most positively with the electrical vehicle market? Some of it, weather events and climate disasters last year, 20 in total, have caused billion-dollar issues and breakdowns in the grid. Couple that with, and I'm going real high level here, the predictive accumulation of EV population through the next, this goes out to 2030 also. So electrification's here, it's coming, it has traction in certain segments and it has mandates in certain segments, and the net result of both is that the business builds up from an EV standpoint. How on earth does America think it's going to provide this energy? Because the grid can't do it. We know that. We've done a real detailed study on this. It just can't do it. If you've got a Class A charging plaza for common traffic, you're looking at the same energy as a small town at any one point in time. So how do we get that energy? And propane can be part of that solution. So we have fledgling EV charging solutions. So technology demonstrated, now we need to scale up, and that's what we're doing. How can this possibly be economical? Bearing in mind the low cost of fuel for your propane, bearing in mind the renewable fuel element as well, so low carbon footprint. Think about the states with the high carbon intensity and how difficult it is for them from a grid standpoint. Overlay the capacity issues, and remote charging is absolutely going to happen. Will they all be propane? No, there's other solutions, but propane enables you to bring in a low cost energy solution, particularly in places where you're remote from the grid. So even if the capacity is there, can you connect? Because the investment in interconnects is huge. So with EV charging, the simple formula is if your electricity prices are above 25 cents a kilowatt hour, peaking at 45, without including the 15% inflation we're seeing in some states, and you can deliver propane between $1.5 and $2 a gallon. Think about our oil to gas, that's $1.70 on that chart. Propane wins, cheapest solution. Lower your emissions, less cost, independent from the grid, existing supply infrastructure. It's just business we do today, and a path to renewable propane as well. So getting that message out to the OEMs is key, because we kind of own this data. It doesn't exist anywhere else. We spent quite a bit of money in 4 or 5 months of our time pulling that together. It's kind of neat to have that algorithm. You can help people save money at the end of the day. Engine product development. Is that a leading to Eric's slide? Yeah, it is. I had a couple of slides after that, which looked to have been taken out. But where I was going with that was the existing engine participants that we have today. We're working with major engine manufacturers. We've got Ford Products, General Motors. We've got a program with Cummins and several other major engine manufacturers that are working with us for the emissions reduction work that I referred to. So it's a very, very healthy time to be active in the propane space. Folks are kind of waking up to the advantages that we offer. So thanks very much for the opportunity to present that. And I guess, do we want to take questions now, Josie, or wait to the end?
I think we'll move on to our panelists from Standardine and KTEC, and we'll look for questions in the chat while they're getting ready for their presentation. So let's welcome Eric Sweets and Srinu Tuduru to our stage here for their part of the presentation.
Yeah, thank you, Alan. Thank you, Gavin. Good afternoon, everyone. We can slide to the next slide, Josie, if you want. So Gavin's covered a lot of the technology or background of propane, the infrastructure. And roughly 3 years ago, KTEC and PERC, who Gavin's associated with, were discussing next steps in propane or technology for fuel delivery. We had some previous experience with port fuel propane, and we're looking at direct injection is quite common and what a program looks like. So we kicked off a evaluation of direct injection propane. And as the program kicked off, KTEC and Standardine became close partners in it, and they came on board. And we'll see through this program how that evolution came and kind of where we ended up at the conclusion. So I'm a lead engineer here at KTEC Engineering. Srinu.
Yeah, this is Srinu Gunturu. I'm the chief engineer for Standardine, and good afternoon, everyone. And thank you very much for the discussion here today. Next. So I'll just cover the Standardine side of it. I mean, for the people who doesn't know what Standardine does, is Standardine is a tier 1 supplier. We design, manufacture, and remanufacture cells best-in-class vehicle and powertrain pumping, injection, and also we do a lot of air and fluid managements and some control solutions as well. Standardine is committed to continue to invest in the development of the next generation technology to support the decarbonization of the ICE engines, and which is internal combustion engines. Our innovations and enable clean combustion compatibility with the low and zero carbon fuels, and to optimize the engine for the hybridization that we believe in, that's going to be the future of the internal combustion engines.
Yes, from KTEC's background, so we're a manufacturing, engineering, and testing facility located north of Detroit. A smaller company that we can act quite quickly and fast with changing technology and development of projects like this, and kind of just in the encompassment of the project, it wasn't just a research and initial study of, hey, here's the results. We're very forward thinking in the desire of commercialization, a quick path to offer this technology, and as we kind of get to the conclusions of it, kind of where we ended up, and that we're quite pleased with Standardine and where all the components and the technology level and where it ended up. So we can go to the next slide. Just a quick bullet line of the points we'll cover through the presentation. Go next. So the first question of why kicking it off is why direct injected propane. Most propane engines are either port fuel mixed, which means they're injected around 100 psi around tank pressure, or mixer, where they're regulated down and vapor mix and can have poor cylinder distribution. So from the direct injected side individually, if you just look at it from a gasoline standpoint, it makes up a large portion of the current on-road vehicle market and a growing off-road vehicle market. It's already highly accepted and has its natural benefits in efficiency and improved emissions, which is why the percentages continue to go up of the OEMs currently using it. Kind of as Gavin's discussed on the propane side, it has its own efficiency gains with the octane rating as well as its emission capability. So bringing those two technologies together, it was an obvious area of why would we not do this? But there were obviously some obstacles that come up through the process, and it's a gaseous fuel, so it's vapor and liquid depending on the pressure and temperature, as well as it's been not as researched of a data point. There's been a few articles written here and there, but from a feasibility standpoint, no one had really looked at tackling it. We can go to the next slide. So the technology started off, or the program kicked off with a non-firing test cell where we were able to benchmark current OEM injectors, pumps, and see what shortcomings a current GDI component would have if you tried to run it on propane. Through this time, we transitioned to a firing test cell. We're able to benchmark an engine on gasoline and then compare it to propane. And we'll cover those results here in a minute. But in that feedback and seeing the shortcomings of the OEM components, we were able to feed that back to Stanadyne and discuss what would a propane-specific pump or a propane-specific injector have. And the initial scope of the program was to just benchmark OEM components, but with Stanadyne coming on board, we kind of were able to skip a step or two ahead and get at and near commercialization of propane components. So we can go to the next slide.
So as Eric mentioned on providing a solution on the fuel systems, and KTEC and PERC reached out to Stanadyne to help on a specific DI pump and the specific DI injector that we have developed to be able to go on the propane engine. And you can see that we took the GM L8T engine as our base engine platform to prove out this concept. And also in the next coming slides, we'll show that not only just proving out the performance of the engine, we have ran some durability up to 250 hours on the engine to prove out that this DI engine is promising for the propane systems. And also it's only few hardware components were changed on the engine. It's only the fuel pump and injector, and the engine was used as is. This technology can be applied for any size of gasoline direct injection engine using the pump and injector and some flow circuits changed were be able to adaptable into any size of the gasoline direct injection engine. Next slide.
So from a power output, we baseline the L8T, which is natively ran on 87 octane, and then reran it with propane DI and the Stanadyne components, flow updates, and then engine controls. So all targets were tested at a lambda of 1. That's important from an emission standpoint. Come the 2027 regulations, enrichment during wide open testing won't be allowed. And with the propane, we're able to easily do that without EGT limits or concerns, and it lets the catalyst work as it should. Current gasoline engines will offer overrate or run at a rich lambda point, which can affect emissions, and come 2027 won't be allowed. In addition, kind of as Gavin had mentioned, the octane rating of propane is 105, and with the DI capability, there's many turbocharged DI engines and other platforms where if you can increase compression or design an engine specific to propane, we would expect to exceed the 87 octane power output even further than just meeting it, as this engine natively is 10.8 to 1 on a compression ratio point. We can go to the next slide. So at the completion of baseline engine calibration on the propane and vapor lock inhibitor components, we were able to run a 250-hour durability cycle. It was comprised of a few different test cycles and tried to mix off-road, on-road, EPA, and carb test cycles. It included shutdown time, which didn't count towards the running time, but allowed for hot heat soak and refueling. And all these things are important to propane, and we'll cover in the next slide, and kind of the obstacles of vapor lock, and one of the reasons that DI propane hadn't been thoroughly pursued until this time. We can go to the next slide.
So just to add to that, I mean, I know we have ran the 250 hours, and everybody's in mind like, yeah, what happened to those components, and is there any wear or anything? That's what we're going to cover in the next coming slides. So we were able to test the pumps and injectors. On the pumps, we haven't seen any change in the pump performance after running for the 250 hours on the propane, and also you can see there is some change in the baseline to where it's just the end of line test measurement error, but there is no change in flow performance of the Stanadyne pump after running for 50 million cycles with the liquid propane. Next slide. And just to add to that, we have sectioned the pump that was ran the 250 hours, and you can see that there was no significant wear noticed on any of the components other than just the contact or sealing marks of the components. but we haven't seen any significant wear, even at the sealing locations. No wear or no cavitation or no any of the tear down parts have any signs of degrading after running for 250 hours. Next slide. We have seen some. There was few injectors of the injector that we have put on change in performance in 250 hours, and we saw some wear due to lift change in our injectors, and we were able to identify what have changed on those, what caused the lift change, and we were able to put some fixes. If you go to the next slide. And as I mentioned, there was no significant wear on any components other than a couple of components, which are armature and retainer, which caused a lift change due to wear. And we did have a design fix already implemented to address this change in the lift and wear of the armature and the retainer. And also, we are already in plans to do further testing, as Gavin mentioned. We're working with OEMs to be able to prove out these permanent corrective actions which are implemented on the wear, and which we already proven out on this wear on a gasoline. So we're just gonna have to prove out on the liquid propane. Next slide.
So that's kind of covered the testing program through the components, kind of the findings from the durability from the engine side. I breezed over it early, but there's no significant wear on the mechanical engine side of it. Often early on, maybe the wording 10, 20, 30 years on propane was, oh, you need to upgrade the valve seats, or you need to upgrade this because it's propane and there's no liquid going over the valves. But modern direct injected engines account for that. The materials and technologies with that have advanced. So there's no valve recession, no wear on the engine side while running on propane, even in a quite stringent test profile. So some of the obstacles that we went through, and one of the key areas was vapor lock inhibiting. So propane being gas and liquid, you're always trying to deliver liquid propane to the pump. And if that fuel going to the pump on its way gets heated to a certain point without a proper rise in pressure, it'll vaporize and you run into this condition of vapor lock. It happens to DI engines, it can happen to port fuel engines, and it's a common concern when dealing with propane. So one of the big projects and areas K-Tech focused on with Standardized supplying the hardware was building a hardware and software system that delivered the propane correctly to the pump and never allowed for a vapor lock condition. The graph on the bottom right kind of shows the green arrow is to the purple line is right where a tank would ride. So as temperature rises, pressure of the tank rises. On a port fuel system, it'll operate in the blue area where they'll have a pump in the tank and try to raise the pressure a few bar or 5 to 10 bar, 140 psi above tank pressure. So that's the same pressure we would deliver to the DI propane pump. And once it got to the pump, we're able to increase that pressure even further, similar to a gasoline engine where it'll run upwards of 100 bar to 200 bar. It's the same as gasoline. There's no safety issues with that pressure, but allows you to run direct injection and inject the fuel direct into the cylinder. So that brings you into the green area, which is a compressible liquid and has no chance to turn to a gaseous fuel. So there's benefit in that. Vapor lock, once you're in the rail, isn't a concern. You're just dealing with the vapor lock going to the pump. So through a handful of valves and control systems and strategy that's not overly extensive, but was implemented and strategy developed to ensure it and ran throughout the test cycle, we were able to deliver liquid propane to the pump at all test conditions. Srinu will mention and discuss kind of some of the pump obstacles we ran into, and some of that was based on the feedback that we had from benchmark components.
Yeah, so just to cover on that topic, we do have to increase the focus on the improving on the volumetric efficiency of the pump, and also have made changes to the injector to have a higher flow than what's currently on the LIT engine, so to be able to deliver the right amount of fuel, liquid propane, to make sure that we get the efficiency of the engine as well. And to add to that, we have added a secondary inlet to be able to make sure that we don't have that vapor lock inside the pump, especially in the plunger and the sleeve area. So, next slide.
So as a summary and conclusion of the technology, the testing, and everything that's kind of gone over the past year or two on this development is, we were able to meet and exceed the torque and performance of the baseline engine on gasoline. So, it's kind of going back to some of Gavin's points. That's check number one. We were able to meet the performance. Reliability, we were able to complete a 250-hour durability test cycle. Obviously, there were notes taken away from that and things being addressed and updated, but the cycle was rigorous. We hit heat soak, hot shutdown, refueling, and hitting on and off road load points. LPG and direct injected emissions show promising results, especially when compared to diesel. The after treatment system is very similar to gasoline, so there's little variance between the two from an upfit or from a manufacturer having or offering both options. Mr. New, I don't know if you want to take the next.
To the conclusions on the direct injection liquid propane gas. We have a high level of efficacy and the reliability we have seen based on the 250 hours of durability testing that we did so far, and also the Standardine, the fuel system technology is ready for the commercialization for the liquid propane gas for the direct injection engines, and also the KTEX developed the vapor lock system solved the concerns of the limitations surrounding the liquid propane on the direct injection technology. And there is also potential, I think, covered a couple of his slides on leveraging the DME blends and renewable propane with this new technology to achieve the net zero carbon emissions. And Standardine and with PERC to be able to have an engine to propose to make sure that we continue the development and have more durability hours to make sure that we take this technology to the commercialization on the liquid propane gas on the direct injection engines.
And then I know Josie mentioned it, that the slides will be shared. On this slide in the bottom right corner is a link to a more thorough the project report for this testing and this program. So those that are interested can have access to that once the slides are distributed.
Sorry, we have to make it so fast so that we can take any questions in the last 10 minutes. So.
Very good. Well, thank you both, Eric and Serena, for that excellent presentation about this really exciting research. Let's go take a look at the questions that we have, and we have a few of them so far. Let's start off with the first one, and I guess this will be for you, Gav. Looking at the genset segment, what is the most representative range of power there?
So gensets, there's an upper limit, and that's really around fuel consumption with established technology. So we tend to say that anything over 400 kilowatt electrical, refueling becomes a major piece of work. You've either got to have huge tanks, or you've got, if it's a prime application, you're getting regular refills. So we tend to see that's where it settles out. So, but the propane power generation market technology spread takes you from, if you look at some of the Kohler product, the small air-cooled stuff, all the way up to large 22-litre V engines developing 350 kilowatts and above. So we've kind of got most of the nodes covered, which was kind of a shock for PERC when I did a breakdown of that. So the task is to get genset OEMs to recognize the fuel as something more than a standby fuel and amplify the markets on the back of that. But yeah, simplistically, if you can think of a node between lower, single-digit kWs up to 350 to 400, then there's a product there that'll cope with it.
Okay. Very good, thank you. Just a reminder to our other participants, please submit your questions via the chat. We have a question here coming in. You've shown the comparison of power and torque between gasoline and propane. Have you compared with propane and port fuel injection, liquid injection on the same engine?
We haven't yet. I would expect similar results to that of port fuel gasoline to direct injected gasoline. So the main benefit being volumetric efficiency gain. And then at, I think, high end of compression ratios and boost ratios, you would slowly get into the addition of, once the port fuel propane became octane limited, you get additional benefit of going to direct injected. So I think high compression or boost ratios, there'd be the secondary benefit on top of that.
Thank you, Eric.
Yep.
Anything else to add on that?
Yeah, there's no oil with the propane injection. It's the same propane you'd get filled at either a refilling station or I don't know, burned in outdoor grills. It's all HTV5 or 95% propane, and then 5% butane and other variants, but no oil or special fuel was used for any of the testing of the durability. Gavin, I don't know if you want to take the renewable propane and quantity question.
Yeah, so typically for propane in internal combustion engines, there's filtration, because we've got to deal with contaminants in the process. It might be in the tank, it might be in the lines, and there's also what we call the heavy and the light ends. When you're refining, some of that gets carried over, and it can be in liquid form. And in earlier engines with a vaporizer with a rubber diaphragm, that's where it would collect typically, and then you have problems. The benefits of direct injection, you don't have that old technology in there. It's way more tolerant. And the filter systems that are used both from a fuel distribution aspect, so when you go to fill up, and then the filters in the fuel system in the vehicle or the application, they're all constructed to deal with any of those contaminants. So it's easy to do. And from a renewable fuel timing, so from a renewable propane standpoint, if you could think back to that chart with a curve that went rapidly upwards on that scale, at least, we're aiming by 2040 to have equivalent renewable propane to conventional propane. DME, I can't speak to with any confidence in that is proliferating as well, but the role of the Propane Education and Research Council is to work with propane, not necessarily directly with DME. The two fuels can be blended, and they do that successfully in Europe because the emissions regulations are different to America, and you can do that easily. How do you see propane in the landscape of future alternative fuels against methanol and ammonia? Propane's hugely viable. It's safe, it's available, distribution network already exists, and the majority of segments that we work with today already use propane. So whether it's in a farm environment or warehouse environment with forklift trucks, it's established. The challenge we have is political and investor concentration on a silver bullet. People like to see things served in the rate that they can scan through a mobile phone when they're reading the news or something. And it's very comforting to think there's this great thing that's coming that's going to fix everything for everybody. It cannot possibly happen. The emissions footprint of fossil fuel propane, even not including renewable, is massively less than hydrogen today, and will remain that way for a considerable period of time. And then you get into the whole infrastructure and availability. Same applies to methanol and ammonia. But it depends on your market. If you're comparing how the requirements of a mobile delivery service, so on road, versus power generation at a data center, versus energy in a construction site that's got a whole worksite mentality. So what's the solution for the whole worksite? That's going to drive different solutions. And for some of those, propane works well, and for others, maybe an alternative solution works well. So it's as technology advances, it becomes increasingly segmented. That's natural to everything that we see today. Is it breaks the market up, and we'll have that with fuels. We're seeing that already. But propane, there's an easier path to emissions reduction with propane than with most of the fuel sources. At the moment, doesn't get the bandwidth from a media standpoint, and that holds us back.
Don't forget to continue submitting your questions here to our audience. In the meantime, I have one. So I think this is really a compelling new research that really positions propane in a way that we haven't envisioned it before, perhaps, and being able to be a really key player in more expansive use and helping to decarbonize different sectors as being an incrementally better choice, both on the emissions side and on the technology side. How do we see the efficiency, and put it in layman's terms here, how many the miles per gallon, if you will, how do we see that shaping up for propane using this new advanced technology from Stanadyne?
Yeah, I mean, with current engine technology, it's meet or exceed gasoline. But as the gasoline technology continues to advance in applying propane and octane rating, I mean, diesel is the current benchmark for thermal efficiency, and that's where we'd expect to get to with propane. Kind of as Gavin nailed, turbocharging will be likely required. You know, advanced engine technology, and then direct injected propane. I think there was a question earlier on compression ignition propane. We might have glanced over it. I don't know if you have any input on that, Gavin, just on the future timeline of widespread adoption of compression ignition for the propane.
Yes, I might have missed the compression ignition bit when it sped through. So let me start with a sweeping statement. For vocational trucks, gasoline is dead, and the engine world was thinking of gasoline as a way to help fix some of the diesel challenges as emissions get tighter, but the greenhouse gas emissions levels wipes out that business model completely. So we kind of in the past we've kind of compromised on type of engine technology to get propane into the market, and then through the work that Stanadyne's doing and others, we're optimizing the ability to overlay more efficient fuel delivery in engine configurations that may already exist today. The next step is the compression ignition piece. That's a good example, along with ultra lean burn, along with refining after treatment, definitely with forced induction. So the target we have now we know gasoline's out of the game, at least for commercial vehicles. The target is to equal diesel. And the building blocks that we've got that include standardized direct injection plus emissions plus internal management of the combustion event. The more you can bring into the combustion event, the less reliant you are on after treatment. And we see that recipe, which I can't go into in detail, as exceeding the efficiency of a diesel engine. So when we get to that point, we forget all of the compromises that propane's had to live with over the last 50 or 60 years. So automotive technology, external conversion kits, we get to a fuel that has a range of engines that were designed in the first place to run with propane and meet emissions and greenhouse gas limits. That will be transformational, because that gets you, take a 5-litre diesel out, put a 4.5-litre propane engine in with a supercharger. It opens things up tremendously.
Thank you, Gavin. We have another question here about request to expand a little bit more about the future application of propane on 2-stroke marine engines.
From a 2-stroke standpoint, I'm not aware of any activity that's developmental for propane. 2-stroke brings with it a bunch of challenges around emissions, typically with, you know, how do you manage the lubricating oil, which is often part of fuel delivery, and that oil contributes to combustion. So you're not just burning the fuel, you're burning an element of the oil as well. So that tends to rule out 2-stroke. So beyond that, and am I aware of any optimization to move away from that type of restriction and limit? I'm not personally aware of anything. I think all the work we're doing is with liquid cooled.
Okay. We have another question here with a global warming potential of 4. How do we handle the leakage during storage, delivery, and operation of propane?
There's some extremely rigid codes and standards around how propane technology is deployed, particularly from a safety standpoint, and obviously leaks leads into safety. So when the Propane Council was established in 1996, established by an act of Congress, and with the aim to educate, so that's help OEMs and customer users of propane to do it safely, and then working with governmental bodies to encode codes and standards. So it is tremendously well regulated, and we have a really, really good safety record, particularly around leaks. The challenge is, and it's a fair point to raise, as you proliferate, and we will, the places where propane is used, how can we be sure that we're capturing all the new potential risks with that? That's part and parcel of what we do.
Yeah, from an engine side, that's not as big of an issue, but tip leakage of DI injectors, just due to the rail pressures paid attention to on shutdown, just that there's not open leaks and potentially poisoning of the catalyst. And then similar on the storage tank with the managing of some of the vapor lock inhibitors, you ensure there's never a overpressure system that would require a tank to vent. Similar to, like, I know often liquid hydrogen tanks will vent, obviously not negative effect to greenhouse gases, but that's managed within a lot of the control system to mitigate that or never allow that to happen.
Interesting analogies. Many a time we've been out in a cars, haven't we, driving around, and you drive past a Shell gas station, and as you drive past with your windows up, even with a carbon filter in your air intake for your ventilation system, you still get that whiff of gasoline. With a propane setup, there is really no vapor escapes because everything's done by positive connection. You're not just vaguely pointing a hose into a tank. It actually physically connects to the tank body, so it's locked. Unless it's locked, it won't deliver. And there's various other safety cutoffs and vent devices that stop leaks. But it's fundamentally different technology, so different to handle, but pretty easy to learn as a user to fill up, but very safe from a leak standpoint. We have real strict regulations around that.
Okay, very good. Well, I want to thank our panelists today for an outstanding session about what propane is, what it can be in the future in terms of helping make our transportation system lower in carbon and more efficient. I think as we all look at where we are today and where we're trying to get to, we see that there's a need really for all kinds of solutions. And this one certainly holds a great deal of promise as an incremental innovation in internal combustion engines that could enable their continued use and expanded use in some of these sectors in the years to come with an established network of fueling and servicing capabilities. So I think as time goes on, we're going to see that level of diversity in the system. And I have no doubt that propane is going to be one of those growing solutions. And hopefully we're going to see more commercialization of this technology from Stanadyne and K-Tech. That's some really great work there. And just a final note here that everyone that is attending today will receive a link to the recorded version of the event. And we will make presentations available from the presenters once they've approved that to go along with that. A little bit of a plug for an upcoming virtual event. Next in our series is dealing with hydrogen internal combustion engines and what that entails. So we have that will be coming up in June. And we hope that you might put that on your calendar and reserve your spot today. With that, I want to thank Gav, Srinu, and Eric for their great presentations today and many excellent questions from our audience. And we wish you all a great afternoon and thank you again for your time.
Thanks.
Thank you all.
Take care, everybody.
Thank you.